also, we couldn't leave that little point at x equals 3 on the x-axis over there by itself. That point was on the curve. The curve had to turn and go back up again. And it couldn't turn again because there are no more x-intercepts for it to go through. So it had to have the 2. Are there situations where you might be guessing whether there were 2 turning points or no turning points? Absolutely yes. And again, in my class, when we do this, if the information you have, the end behavior information, the x-intercepts, and the y-intercept, doesn't help you determine whether there are 1 or 3 turning points or 2 or 4 turning points, then as long as what you draw for your sketch goes through the points and has the proper end behavior, and the number of turning points is one of the possible correct answers, even if the actual graph is incorrect, you're right, because until we get to calculus, or unless you get a graphing calculator and do it on the graphing calculator, you will not know. But the key thing is we have to base our possible sketch on the end behavior, the x and y intercepts, and the possible number of turning points. Those are the 4 things we can do. Okay? And of course, this gives you a good reason to understand why the study of calculus is so important, because of calculus will show us an accurate picture of the curve, and if we're interested in knowing about the curve because we're using it as a model for something in our business, scientific, engineering, governmental, or whatever organization we're working with, then certainly a knowledge of calculus can be very, very helpful. Obviously, we wouldn't do it by hand. We'd probably have a computer do it, but quite frankly, understanding what the computer is doing, it certainly helps to have the mathematical knowledge to ensure that you understand what is going on. Okay, let's take a look at the next visual. The next visual gives us another function, y equals x cubed plus x squared minus 5x minus 6. And step by step, we're going to go through and work this problem. And then we will look at one more problem, and we'll see if we have time. Perhaps I'll give you some work to do when we shut the tape off. The first thing we do, of course, is to get the y-intercept, which is at 0, negative 6. The constant term is negative 6. Then we get the zeros. We look over here and we say, hey, the constant term is 6, the lead coefficient is 1. The only possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. It turns out that negative 2 is the one that works. And when we divide synthetically, we get a quadratic that yields 1 plus or minus the square root of 13 over 2. So there are our 2 irrational answers plus our negative 2, our rational answer. The last 2 lines on this visual help us to sketch, because taking a calculator of any type, as long as it does square roots, we can figure out that 1 plus the square root of 13 over 2 is approximately 2.3. Those wavy equal signs mean approximately equal to. Okay, close enough, 2.3. And 1 minus the square root of 13 over 2 is approximately negative 1.3. So now we have our y-intercept, negative 6, our x-intercept, negative 2, and 2 approximate x-intercepts, 2.3 and negative 1.3. And we can go to the next visual, which has the function again and the graph. Notice the y-intercept at negative 6. Notice the 3 x-intercepts at negative 2, negative 1.3, and a 2.3. The end behavior. Once again, we have an odd degreed function, positive lead coefficient, going up as x increases, going down as x goes to the negative end of the world. And again, we have to have either 2 turning points or no turning points. Looking at the fact that we have those 3 x-intercepts, it would be impossible to have no turning points. You couldn't draw this kind of curve through those 3 x-intercepts and have no turning points. The only possibility is 2 turning points. Where those turning points are, you're not sure. I mean, obviously, one is between the negative 2 and the negative 1.3, and the other one is between the, probably between the y-axis and the x equals 2.3, but that's irrelevant. This is a good enough sketch. It might, in fact, not even be absolutely right, but it's close enough for what we want. It utilizes the knowledge that we have. So let's look at one more. The next visual shows us y equals x cubed minus 10x squared plus 25x. What's different about this particular one? So far we've looked at cubics. What's different here is it has no constant term. What does that mean? Well, that means the y-intercept is 0. But if the y-intercept is 0, that means the curve goes through the origin, where y is 0 and x is 0, which means we've also found one of the zeros. X is 0 is a 0 of the function. When x is 0, y is 0. So it's both a y-intercept and an x-intercept. Well, what I've chosen to do here, as I show you on the second line, which is highlighted, is to factor out the x in x cubed minus 10x squared plus 25x. I've done that to remind us that when we studied factoring, we talked about the common monomial factor. And now we have x squared minus 10x plus 25. We can do that by factoring or use the quadratic formula. And when you factor, you get x minus 5 times x minus 5, which means you get x equals 5 twice. So you really have 3 answers, but 2 of those answers are the same. And look at the graph. Notice that we have only 2 x-intercepts, 0 and 5. And look at what happens at 5. At 5, not only is it an x-intercept, it is also a turning point. How did we know that has to happen? Well, we look at the end behavior. Again, positive lead coefficient, odd degree. It must be going up as x increases to the right. The function must be going down as x gets more and more negative. It has to go through the origin. It has to turn to get back to the x-axis at 5. If it goes through the x-axis into the negative area below the x-axis, to turn back up for its final end behavior, it would have to go through the x-axis again. But there are no other x-intercepts. So what happens there is, because we have an answer, a 0, what's called a root of multiplicity of 2, that is, it occurs twice, what happened? The x-intercept at 5 is also the turning point, and we thus have our graph. We can say, wait a second, we've only looked at cubics. How about other situations? Let's look at another situation right now. Let's erase the board and take a look at a 4th degree polynomial equation. How about y equals x to the 4th minus 16? I've selected this for a very special reason, as we'll see. What am I going to do? Well, let's see. We can do this many ways. We can do it by factoring, but let's do it using the synthetic division. Well, we have 1, x cubed is 0, and 0x squared, 0x, and negative 16. Let's choose, how about a 2? 2 is a factor of 16. And we get 1, and 1 times 2 is 2. We add, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And what we have is an answer. X equals 2 is a solution, is a 0. Let's try negative 2. Why am I trying negative 2? Well, first of all, it has to be a factor of 8, but also I know the answer is negative 2. And of course, I could have found this. You notice this is the difference between 2 squares. And if you want to do it that way, you should get the same answer. So we have 1, negative 2, 0, 0, 4. 4 times negative 2 is negative 8. And as promised, this is also a 0, the polynomial. We have 2, negative 2, and now we have x squared plus 4 equals 0. Solving that, we can just go ahead and bring the negative 4 over here. Take the square root of both sides. What's the square root of negative 4? It's an imaginary number. X equals plus or minus, 2 possible square roots, 2i. Since 2i times 2i is negative 4. What does it mean if we have these 2 imaginary answers as zeros? Well, let's take a look. Let's go over to the easel and see what this sketch is going to look like. Let's draw our axes. And we have, what do we have? We have y equals x to the 4th minus 16. The first thing we know is that negative 16 down here someplace is the y-intercept. We also know that, let's see, we have x-intercepts at 2 and -2. This is 2, here's -2. The other two values for the zeros of this polynomial are imaginary, which means this is the only two places where this function crosses the x-axis. The end behavior, even degree, positive lead coefficient, both are going up. How many turning points can we have? We can have one less than 4, which is 3. Now, maybe you could figure out how to put 3 turning points in here, but with only 2 x-intercepts, I'm not sure if that's going to work. But we know it could also be 1, that is 2 less than 3. One turning point would make this look like a parabola, which would fit everything absolutely perfectly. Through here and up through here, and there we go. And in fact, that's what the graph looks like. If you're creative enough, you might be able to put, maybe you may be able to put 2 more turning points in there. And it wouldn't be wrong if you did it so you had 3 turning points with the correct end behavior, the 2 x-intercepts and the y-intercept. So there's an example of a 4th degree polynomial. Now, obviously in your textbook you should find many examples of sketching polynomial functions. It's quite important. And sticking in the realm of sketching graphs, our next lesson, lesson 22, is going to take us into something new, sketching rational functions. And knowing how much fun you had in this lesson, I know you can't wait for lesson 22.